Hello, this is Miraj Patel here, and today we're going to be talking about simple harmonic motion, and we're going to be introducing waves. So these are totally new topics, and so let's begin. So what is simple harmonic motion? Simple harmonic motion, or SHM, is a motion that repeats itself because a force always tries to bring the object back to the equilibrium position. So this basically means it's a cyclical motion that always keeps on repeating itself. And in simple harmonic motion, there's three things you need to know, or important vocabulary. There's a period, frequency, and amplitude. The period is the time it takes for one complete cycle to occur. So basically a period is how long it takes for the whole thing to happen once. And it is measured in seconds per cycle. So seconds per cycle. The frequency, as most of you probably know, is pretty much how frequently it occurs. So it is the measure of how many cycles happen in a given amount of time, and usually we want to know how much it occurs in 1 second, and that is a hertz. So cycles per second is a measurement, and that's hertz. So hertz is a measure of frequency. So if something is 2 hertz, it's 2 cycles per second. So this is what the measure for frequency is. And notice that the units for frequency is a reciprocal of the period, because period is seconds over cycle. Frequency is cycles over seconds. So because they're reciprocals, frequency is a reciprocal of the period. So if you put 1 over the period, you get frequency. If you put frequency over 1, you get the period. So this is going to be very useful when you're using the formulas. And the amplitude is a maximum displacement away from the equilibrium position, and it's measured in meters. And if it's very small, most of the time it's in centimeters, but you can convert it to meters. Okay, so one of the most common simple harmonic motion scenarios is a spring and a box, or a ball. So a spring always tries to pull the box, or the object it's attached to the equilibrium position, and it'll always try to pull, or pull it to the equilibrium position. And when a spring is pulled or pushed and then it's released, the box will have the greatest kinetic energy as it's passing through the center, and the least on the sides. So here we have the spring. So equilibrium position is this line here. And so, okay, let's just say this spring is moving downwards towards this position. In the middle, while it's moving back and forth, it'll have the greatest speed, so greatest kinetic energy. And then it gets all the way to the bottom, stops. This has a lot of potential energy. And then it'll go back, speed up in the center, and then move up to the top here. And again, it'll have the greatest potential energy, again, because it's at the greatest amplitude. And so this little thing here just says that's the amplitude. So that's the maximum displacement. So these two have only potential energy. This one has a lot of kinetic energy, assuming that it's moving between these two places. So between the amplitude and the equilibrium, it's accelerating. So let's just say we're at equilibrium and we're going downwards. The spring, the ball, is it's slowing down. So from here to here, the ball is slowing down, then it stops, then again, on the way back, it speeds up. At equilibrium, it stops accelerating. So because equilibrium, you're at the fastest point. Then again, after it passes the line and it's going above, then it slows down, stops again, and then speeds up. So between this point here and this point, it's speeding up, then it stops at the end, stops accelerating, then it goes back in the negative, it goes upwards and it speeds up here, and then it stops accelerating here, but still moving fast, then it slows down, so it accelerates in the opposite direction and then stops. So after a while of doing these problems, you will understand exactly what I mean. And this is sort of like, it makes sense when a spring is, pulling and resisting. When it's going the fastest in the middle and it's going to stop, it's slowing down. When it's opposite, it's stopped and it's going to the middle, it's going to speed up, and then the same thing around. And then using energy, you can figure out the speed of the spring or the ball in the center at equilibrium while it's moving. And you can also figure out, if you know the speed, you can figure out how far it'll go with energy, using energy principles. So this is sort of going to be a repeat if you've been here or if you've done energy. And so we're just going to do one problem. It won't be hard. So an ideal spring with a spring constant of 500 Newton per meter is stretched out to 5 centimeters and released. How fast does a 3 kilogram block travel as it passes through the equilibrium point? So imagine we have a spring, we pull it 5 centimeters out and let go. And the block weighs 3 kilograms. So we want to know how fast it's traveling at the center. So we're going to use the conservation of energy, which is basically this little statement. The sum of the potential energy in the spring equals the sum of the block. And since we know this is ideal spring, which is given in the problem, we know that energy is conserved. So we can use this statement here. So the potential energy of a spring is 1/2 kx squared, where k is the spring constant and x is the distance away from equilibrium. 1/2 mv squared is kinetic energy, where m is mass, v is velocity, and that's it. So I'm going to cancel out the 1/2 by multiplying each side by 2, so it cleans it up here. And we want to solve for velocity. So let's divide both sides by m first. Then since v is squared, we take a square root. And since this x squared is within this square root, I can take it out and leave it right outside, and we'll just have this statement here, which equals velocity. And this is all from the conservation of energy. So we just substitute it in the two energies and solve for the one we want. And so if we do this and plug in what we know, the displacement was 5 centimeters or 0.05 meters. The K, or the spring constant, is 500 newtons per meter. And then the mass of the block was 3. And if we plug this in, so you do 500 divided by 3, then take the square root of that and then multiply by 0.05. And you would get 0.645 meters per second. So that is how fast the block moves at its fastest speed, which is as it passes through equilibrium. Now we're going to talk about a period of a spring, and remember, the period is how long it takes for one complete cycle. So basically, if you pull the block, let go, how long does it take for the block to come right back to your hand? So that is the period. So the formula for the period is 2 pi times the square root of m over k. So notice in this formula there is nothing related to amplitude. So the time it takes for a spring to make a cycle is only affected by the mass and the spring constant, not by how far it moves away from equilibrium. So this is saying that if I pull a spring 1 meter away from the equilibrium or 5 meters away, even though I pulled it much farther the second time, it will take the same time for the spring to come back to me if I pull it and then keep my hand there than if I pull it only 1 meter. So that's kind of weird, but the spring will take the same time regardless if it's the same mass and same spring. So so the reason why is because when you pull a spring harder, it pulls back with the harder force. So it's going to accelerate much faster, and it's going to, even though you pulled it a greater distance, it's going to accelerate so much faster that that acceleration increases the speed. So it can make the same distance or the same a longer distance in the same amount of time. And if you pull lighter, it doesn't accelerate as much. So that's why if you pull 1 meter and 5 meters, even though you pulled 5 meters more or 4 meters more on the 5 meters, um, it will take the same time for both of them to reach back or make one complete cycle because of how the spring works. And so let's just do some hypothetical scenarios. If we quadruple the spring constant, so if we multiply this by 4 on the bottom, we will half, 1/2 the period. So to prove that, or to show how that works, is let's just say we have the square root of m over k. So I did not include the 2 pi because it's a constant. So, so I just got rid of that. Now if we add 4k for the k normally, so if we put a 4 in front of the k here at the bottom, if we take the square root of this 4, or 1/4 technically, because there's a 1 on top and 4 on bottom, if we take the square root, we will get a 1/2 outside. So this is m over k, the square root of m over k. This is 1/2 square root of m over k. So the period was half. And that makes sense because the spring is more stiff, so it's going to pull much harder if the k is greater. So this is why the period decreased, because the spring got stiffer. If we quadruple the mass, we double the period. So the same thing, if we have m over k, the square root of m over k, I got rid of the 2 pi because it's a constant. Now if I add 4m inside the radical for m, then if I take the square root of 4, I just get a 2 outside, and the same thing happens. We have 2 times the period if it was normal. So, so basically, if we increase the mass, if you remember from dynamics, if we increase the mass, the acceleration's less, because force equals mass times acceleration. If mass is increased, acceleration is decreased if the force is the same. So it won't speed up as much, so it can't cover the distance as fast. So the time it takes would increase. And so that is how that works. So now we're going to talk about the second type of simple harmonic motion that's very frequent, which is a pendulum. And a pendulum, it also has amplitude, period, and frequency. And the amplitude of a pendulum is basically just the angle it goes, how far it moves. And the reason why a pendulum is a simple harmonic motion is because gravity, a component of gravity, always tries to pull the pendulum back to equilibrium. So that is why. And just like in a spring, the pendulum has the greatest kinetic energy at the equilibrium position when it's passing through it, and greatest potential energy at the displacement. And at the greatest displacement, the acceleration is the greatest uh, because there's a great amount of force that's trying to pull it downwards. And the acceleration is 0 at the end. I mean at the equilibrium point, which is in the center. So imagine this with me. So we have a pendulum, we pull it back and let go. So let's pull it back to this side, to the right. So when we let go, it's going to accelerate a lot here, but as it slowly reaches the bottom, it's not going to accelerate as fast. Then it's going to stop accelerating once it hits equilibrium. So now it stopped accelerating for a split second, for like that one moment. Then again, it starts accelerating in the opposite direction. So it's going to stop right here. Then it speeds up again. So it's going to start accelerating with it. Stops accelerating here. Fastest velocity. Then it's going to slowly slow down. So it's accelerating the opposite direction. And then it stops. So speeding up, fastest speed, slowing down, stopped, speeding up, fastest speed, slowing down, and then again stopped. So this is what a pendulum really does. So now we're going to talk about the periods of a pendulum. And the period of a pendulum, or T sub p, I forgot to mention, the period is represented by the letter T, and then the subscript is just for pendulum, equals 2 pi times the square root of L over G. So this is important, that a pendulum's period does not contain mass, and nor does it include amplitude. So the period of a pendulum is only affected by how far, or what the length of the pendulum is, and the gravity. It's not affected by the mass because gravity affects all masses the same. If you remember from energy, remember if we drop two objects, or even from kinematics, we did not have mass in any of the formulas because gravity affects all masses the same. It is always going to be like that. Gravity will accelerate you the same, the bowling ball the same, a 10, like a very, very 10-ton truck the same. Everything accelerates the same. If you drop two objects, they will fall the same theoretically. But the reason why things don't, like a piece of paper doesn't fall the same speed as a bowling ball, is because of air resistance, but that's a different topic. So this is important that you know gravity affects all objects the same, so a mass of a pendulum does not affect the period. So if we quadruple the gravity, what will happen is that the period will be halved. And the reason why is we do the same analysis as we did with the period of a spring in a box. Is we have square root of L over G, and I took out the 2 pi because it's a constant. So now we add 4G for G instead. And then if we take out the 1/4 and take the square root, we'll just get a 1/2 outside. This is why the period is halved. And this makes sense because if gravity increases, the pendulum will be quickly accelerating downwards. So it would want to swing quickly back and forth. But if we reduce the gravity, so if we put a pendulum on the moon, let's just say, the gravity would be much less, so it wouldn't fall as quickly as if it's on Earth. So if we increase the length, so if we quadruple the length, the period is doubled, and I'm sure now you know how to do this. So we compare it with the original, so let's just have square root of L over G. And now we add 4L for the length, so we quadruple the length. And then if we take the square root of this 4 here, we pull it out and we get a 2. And so we will get 2 times the square root of L sub G, L over G. And this is double the period of it when it was 1L. And the reason why I chose 4 in all of these problems, or on all of these analyses, is because 4 is a perfect, it's a square root, is a perfect root, so it'll make it easy to take a square root. That's why I chose 4. And even if the problem asks you if gravity was 1/2, you do the same thing. So let's just say, like, you make, instead of putting 4g for g, you just put 1/2 at the bottom. And you can use your calculator to take the square root of that and pull it out. So this is how you do analysis on problems where they don't give you numbers, but they just tell you gravity was 1/2, gravity was doubled. You just plug it in, and then you compare it with what it was originally. So this is how you do it. So let's just quickly talk about the energy. And it's important, especially if you're taking AP Physics 1, they will gladly probably ask you about a graph on the AP test, or your exam or quiz, whatever. So remember that in a pendulum and a spring, if it's ideal and there's no air resistance, the total energy should stay the same always. And the kinetic energy, remember, at the amplitude, so negative and positive, is 0. But the potential energy is at its greatest. And then as it slowly travels from left to right, the kinetic energy increases. It's the fastest at the middle, then it slows back down as it goes to the other amplitude. And this vice versa with the potential energy. At the end it's the greatest, in the middle it's the lowest, and then it climbs back up, the potential energy. So this is how it looks. So now we're going to talk about waves. So waves is pretty fun because it's relatively simple and straightforward. So a wave is energy traveling through a medium, or basically a material. So a medium is just a material a wave is traveling through. There are 2 types of waves, transverse and longitudinal waves. So a transverse wave, or transverse waves, are waves that have displacement that is perpendicular to the direction the energy is traveling. So it's basically like a squiggle or sinusoidal. So it's like a snake. So this is the most common waves most people think of. I'm sure this is what you thought of when I said waves. And so here we have a crest and a trough. So a crest is the top of a wave, trough is the bottom. The displacement is how far the wave travels from the equilibrium position, which is the center here. So the displacement, or the amplitude, is the distance the wave is the farthest distance the wave travels away from the equilibrium. And the wavelength is the distance, or is the length of one complete cycle of a wave. And so it's important when you look at wavelength that you make sure the wave is doing the exact same thing that it's doing on the next point you look over. So from here to here is one wavelength here, because the wave is going up here, and we keep on going until the wave is going up again. So this is a wavelength, but a wavelength, most students might think that from here to here is a wavelength. So this point, it's going up, but this point here, it's going down. So the wave isn't doing exactly the same thing. So this is half a wavelength. But a wavelength is when 2 points where the wave is doing the same thing and the distance between them. So most of the times wavelength is labeled from two troughs or two crests. So crest to crest, trough to trough. But if you're measuring a wavelength from the middle, make sure you're at the same position on the wave. So if you're here, a little past the crest, don't measure in front of the crest here. Measure after the crest here where the arrow touches the top. So wavelength is any 2 points on the wave, consecutive points that are doing the same thing, and the distance between them. So that's a wavelength. It's the length of a wave. A longitudinal wave, or longitudinal waves, are waves that cause a displacement of a medium in the same direction as the energy is traveling. So it's basically a compression like an accordion. So the most common types of longitudinal wave is a sound wave. So as sound travels through the air, it's compressing the air particles. And so here, notice we have a compression here, and this is the rarefaction where it's not really compressed, it's all spread out. And the wavelength would be the distance between the compression to compression, refraction to refraction, or you can do the edge of the compression to the next compression's edge. Those are both wavelengths. So wavelength is the same point to the next same point on the next segment of the wave. So that is the two types of waves. And then transverse waves is what light is a transverse wave. And so transverse waves move back and forth. And velocity is something that a wave has that simple harmonic motion does not. So simple harmonic motion and waves both have frequency, period, amplitude. Waves have wavelength and velocity, unlike simple harmonic motion. So assume you have one wavelength. So imagine one wave. So like look at the top of this PowerPoint slide here. Imagine you have one wave. So you know how velocity is distance divided by time. So if we want to find the velocity of the wave, the distance of the wave is the wavelength, and the time it takes for the wave to travel is the period. So just think of wavelength as the distance of the wave, and period is how long the wave is. So so that is the wavelength and period replaced for distance and time. So since we know that wavelength and period, this is what they are. Lambda represents wavelength, and then T represents period. And since we know that period and frequency are reciprocals, the reciprocal of period is frequency, or so period equals 1 over frequency, and then frequency equals 1 over period. So since we have the period in the bottom of the fraction, this is basically, if we substitute for 1 over f, we have 1 over f in the bottom, and since we can't have fractions in the bottom, we use we keep the first fraction, so we keep lambda at the top, and then we multiply it by the reciprocal of the bottom. So the reciprocal of 1 over f is f over 1, or just f. And this is how we get our formula. Velocity of a wave equals wavelength times frequency. So this is the only formula you need to solve for waves. So for waves, this is the only formula you need. So great news, waves only requires one formula. And two things you need to know for waves. So the velocity of a wave only depends on the medium of the wave or the material it's traveling through. So if a light travels through air, the velocity in air is fixed. So it will always be the same because it's the same medium. But if it changes medium, it'll change speed. And then another thing you have to know is the frequency of a wave is controlled by the source. So if I tap on a table, or if I tap on something, like I'm clicking my pen here, the frequency of the noise is dependent on my finger, which is the source. So my pen controls the frequency you hear. Even if you're hearing through water, you will hear the same exact frequency. So if frequency did change over distance, which is not true, that means that music would sound differently if you were farther away from the speaker. So if, let's just say you were at a concert and your friend is playing the piano and you are in the high seats far away from your friend. So if frequency did change, that means you will hear totally different notes than what he's playing, which is not true. So frequency is only determined by the source. So that's great for music. And so this means that if a wave changes medium, the wavelength will change. Because the frequency is fixed, because it's dependent on the source, the velocity of a wave is affected by the medium. So if we change mediums, we will change velocity. And since velocity equals wavelength times frequency, the frequency won't change, but the wavelength will. So before I continue, this is an example. Basically, the frequency of water, a light in water, is different, or the wavelength is different because of the velocity change as it hits the air. So basically, light travels slower in water, and so when it gets into the air, it travels faster, and the wavelength changes. So that's why it causes the appearance that the pencil changed. So here we're just going to do one simple problem to show you how to do a wave problem. So a guitar string is vibrating at 440 hertz. The length of the string is 1 meter. How fast is the wave traveling through the string? So, okay, so here, imagine that we have a string on a guitar like this, and it's vibrating back and forth. So 440 cycles per second, or 440 hertz, and it's 1 meter long. So we have our formula: velocity equals wavelength times frequency. So because this is 1/2 a wavelength, the wavelength is really 2 meters. And the reason why this is 1/2 the wavelength is one whole wavelength is like this. So we have the bottom and then the top. So in this guitar, we only have the top. So we have to multiply this by 2 to get the whole wavelength. So to get this whole S curve. So the whole wavelength is actually 2 meters, and the frequency again is 440. So if we multiply those together, we will get our velocity, which is 880 meters per second. So this is the speed of the wave on this guitar. And so for strings, it's important to know that tension affects the speed of the string. So if we have a tighter string, the string can vibrate much faster, and it'll actually make higher pitched noises. So that's why when you put your fingers on the guitar and move them closer to the soundboard or the hole, it'll sound higher pitched because the string is tighter and it's vibrating much faster. So that's what causes higher pitches. And so this is all we have for today. So thank you for watching my video. So today we learned about simple harmonic motion and we introduced waves. and tune into the next video to learn more about waves like Doppler shifts, resonance, uh, in phase, out of phase, harmonics, other stuff like that. Uh, Please be sure to practice your knowledge. Visit Rice University's OpenStax College Physics book. It's free. It's online, so as long as you have a computer, you can access it. Uh, there will be a ton of problems for you to practice. You just look in the table of contents and find waves, and you'll find a bunch of problems. Uh, Please, if you enjoyed this video, please spread the word and like this video. And email me any questions and comments at mpatelbuccaneer@gmail.com. I will be glad to answer any questions you have on anything related to physics. Um, and please, for chemistry tutorials, visit buccaneerchemistry.weebly.com. And on that website, there's a link to my email, so if you ever forget, visit my website. Thank you for watching, and I hope to see you next time. And keep on practicing.